Welcome to today's Explainer, everyone. Today, we're diving into something really fascinating, the physics behind how things rotate. We're not just looking at how things move in a straight line anymore. So if you've ever stopped to wonder about the hidden mechanics of everyday objects, you are absolutely in the right place.
Here is a quick look at our roadmap for today. We'll start with number 1, what is a turning force? Then we'll hit 2, the math behind the moment. After that is 3, the rules of equilibrium, followed by 4, center of gravity and stability. And finally, number 5, real-world physics in action.
All right, let's jump right into section 1. What exactly is a turning force?
Up until now, your studies have probably focused a ton on linear dynamics. Things moving straight forward or backward. But we're shifting gears today to the equally important physics of rotation. And to really get this, let me ask you a quick question. Why is it so incredibly hard to push a door open if you press right next to the hinges, but practically effortless if you push out by the handle? Have you ever actually stopped to think about that everyday mystery?
Well, the secret to that little mystery is our main concept for today, the turning effect of force. When a force tries to rotate an object around a fixed point, it creates this turning effect. You'll actually see this referred to in your textbooks as the moment of force. The big takeaway here is that a force doesn't just push things in a straight line. It literally has the ability to make things spin.
Moving right along to section 2, the math behind the moment.
So how do we actually calculate this? It's honestly a beautifully simple formula. The moment, which we call m, equals the force, F, multiplied by the perpendicular distance, d. So m equals F times d. This little equation tells us exactly how much rotational ability a given force has. And since we're multiplying newtons of force by meters of distance, our standard unit is simply the Newton meter.
And this right here is exactly why that door handle trick works. Think about it. If you push near the hinge, you have a very low distance, which means you have to apply a massive, high force just to get enough moment to open the door. But if you apply a low force at a high distance, like out by the handle, it generates a large moment, making the rotation super easy. The distance is literally doing the heavy lifting for you.
Now, we do need to be super precise about one thing. That d in our formula isn't just any random distance. It is strictly the perpendicular distance from the line of action of your force straight back to the pivot. And the pivot is just the fixed point around which the object rotates. So in our door example, the hinges are your perfect pivot point.
Which brings us to section 3, the rules of equilibrium.
Okay, so what happens when you have multiple turning forces acting on something all at once? Well, first, we have to recognize that forces can rotate objects in 2 opposing directions. It's exactly like reading an analog clock. A clockwise moment rotates the object in the same direction as the hands on a clock, and an anti-clockwise moment pulls it right back the other way. It's basically a constant invisible tug of war.